Hello everybody, and you are welcome to our new lecture in flight mechanics. The aircraft equations of motions are nonlinear differential equations. They can be solved with a variety of numerical integration techniques to obtain time histories of motion variables, but it is nearly impossible to obtain closed-form solutions. Because valuable insights can be obtained from closed-form solutions regarding the dynamic response of the aircraft, the following analysis will use a small perturbation approach to linearize the equation of motion and facilitate the definition of closed-form solutions.
Here are the different sets of the airplane equations of motion developed previously. They can be linearized using the small disturbance theory. In this theory, we assume that the motion of the airplane consists of small deviations about a steady flight condition. Each motion variable, Euler angle, force, and moment in the equations of motion are redefined as the summation of a steady-state value and a perturbed value. In many cases, the small disturbance theory yields sufficient accuracy for practical engineering purposes. All the variables in the equations of motions are replaced by a reference value plus a perturbation or disturbance. For convenience, the reference flight condition is assumed to be symmetric and the propulsive forces are assumed to remain constant. In other words, with the assumption of wings level straight line flight for the initial trim or steady state condition, this implies that V0 equal P0 equal Q0 equal R0 equal phi naught equal epsilon naught equal 0. Moreover, if we initially align the x-axis so that it is along the direction of the airplane's velocity vector, which is called the body fixed stability axis, then W0 is also equal to 0. At this point, it is reasonable to ask if the restrictive assumptions of wings level straight flight will restrict our study of aircraft dynamic stability characteristics. Fortunately, the answer is no, because the fundamental dynamic modes of the aircraft are still present, with these assumptions and dynamic stability characteristics observed about a wings level straight line trimmed flight condition are representative during maneuvering flight. In short, these assumptions and choice of body fixed stability axis system have allowed simplification to the equation of motion to a manageable form so that understanding of dynamic stability concepts can be maximized. The following four-step approach summarizes the linearization techniques. Step 1. We cast each variable in terms of a steady-state value and a perturbed value. Assume small perturbations, multiply out and use trigonometric identities. Step 2. Apply the small angle assumption to trigonometric functions of perturbed angles. Cosine theta, for example, will tend to 1. Sine theta for small theta will tend to theta in radians. Step 3. Assume products of small perturbations are negligible. Step 4. Remove the steady-state equation from the perturbed equation. The remaining perturbed equation is a linearized differential equation with the perturbed variables as the unknowns. Step 2 and Step 3 may be interchangeably applied according to the required simplifications. Let's have an example. Linearize the following nonlinear differential equation: C dot equal A times B times sine omega. Applying step 1 by recasting each variable in terms of a steady-state value and a perturbed value, we get the following. A will be equal to A1 plus a perturbation small a. B equal B1 plus a perturbation small b, and so on for C and omega. These are the variables in our nonlinear differential equation. Substitute these variables into the original equation and multiply out. We get the following. For example, C dot, when substituted with C equals C1 plus the small c, so now the result is C1 dot plus C dot equal A will be replaced by A1 plus small a. This is the perturbation value times B. So B will be replaced by the steady state value B1 plus the perturbation value B times sine omega. This is the steady state omega plus the perturbation, which is a small omega. So when multiplying out, we get this line. So with more simplification, or after extracting this trigonometric function, so sine omega capital 1 plus omega small, it will equal to sine omega 1 cosine omega plus cosine omega 1 sine omega.
Applying step number 2 by applying the small angle assumption to trigonometric functions of perturbed angles, and we get the following. Cosine omega will be equal to 1 and sine omega for small omega will be equal to omega in radians. So this equation will be as follows. This sine omega is turned into omega, and this cosine omega is replaced by 1. Then applying step number 3 by assuming products of small perturbations are negligible, we get small a times small b will be equal to 0. First we will get rid of the term a times b. So we get the following. So we'll get rid of a times b, and this equation will be as follows. Then after multiplying out, we get rid of a times omega and b times omega, because both of them are small quantities with respect to the other expressions. So a times omega and b times omega, and finally get the following. So only these terms are remained in our nonlinear differential equation. Then applying the last step, step number 4, which is to remove the steady state equation from the perturbed equation, these two terms are equal since they represent the original equation at steady state condition. C1 is equal to A1 B1 sine omega 1. Remember that the original equation was C dot equal A times B sine omega. So when substituting with the steady state conditions, which is C1 and A1 and B1 and omega 1 in this equation. So we can cancel out C1 with A1 times B1 sine omega 1 because they are equal. So we can cancel them out from the perturbed equation to get the linearized differential equation to be as follows. C dot equal A1 B sine omega 1 plus AB1 sine omega 1 plus A1 B1 omega cosine omega 1, which is the linearized form of the differential equation in terms of the perturbation variables A, B, C, and omega. So our new variables are these perturbation values, this B and this A and this omega. All other variables like A1 or omega 1 or B1, all of them are numerical values at the steady state conditions. Only we have the new variables in our linearized equations are a, small b, small c, and small omega. This is our linearized differential equation. Now, if we introduce the small disturbance notation into the equations of motion, we can simplify these equations. As an example, consider the x-force equation. So this x is a force in the direction of the x-axis. This is the x-force equation we got before. Applying step number 1 of linearization by substituting the small disturbance variables into this equation yield the following. Notice that each variable is replaced by a steady state value and a perturbation variable. So this x is replaced by a steady state variable, x naught, plus a small perturbation variable. And the same for theta is replaced by theta naught, which is a steady state value, and a perturbation variable delta theta, and so on for u and for q, w, r, and v. So this equation is the same like that equation after replacing each variable with a steady state value and a perturbation variable. Using the pre-mentioned symmetry assumption and aligning the body x-axis with the velocity vector, so we will nullify these variables in x-force equations. So each W naught or V naught or B naught and so on will be replaced by 0 because of the symmetry assumption and the other assumption to align our body frame system of axes to the stability system of axes, in which the x body axis is coinciding to the free stream velocity vector. Applying step number 3 of linearization process to neglect the multiplications of small perturbations, we get this simple version. So when multiplying delta q times delta w, this is the small quantities, so we will neglect these terms. Also delta r times delta v. So after this simplification, we get the following equation instead of this equation. Then applying step number 2 of linearization process to make use of the trigonometric identities. So we can take the expansion of sine theta naught plus delta theta and be replaced by the following expressions. Afterwards, cosine small angle will be replaced by 1 and sine small angle will be replaced by the angle in radians. Then substituting in the x-force equation to obtain the following. Applying step number 4 of the linearization process to remove the steady-state equation from the perturbed equation. The steady-state equation can be obtained by setting all the perturbed variables to 0 in the perturbed equation. So, this is the steady-state equation. X naught minus mg sine theta naught equals 0. Because the original equation is that one, so when replacing each variable in the original nonlinear differential equation, so this x will be x naught, and this theta will be theta naught, and this will be u naught, okay, and q naught, and w naught, r naught, v naught, and all of these variables, we agreed that the assumption of symmetry and by coinciding the x-body axis to the stability axis, so we get rid of all of these nodes, so the right hand side will be equal to 0. So this is the steady state equation. So we can get rid of x naught and mg sine theta naught from this equation. This reduces the x-force equation to the following, which is the linearized form of the x-force equation in terms of the perturbation variables delta x, delta theta, and delta u dot. Applying the same procedure to the sixth equation of motion, the linearized longitudinal equation of motion become as follows. These are the three equations representing the longitudinal equation of motion. And the linearized lateral equations of motion will be as follows. These are the three equations of motions representing the lateral motion. So the first one here representing the L, which is the rolling moment equation, and this is the force in the direction of the y. This is the y force equation, and this is the yaw motion. This is the rotation or the moment about z-axis. And these three equations represent, the first one represents the x-force, which we discussed in details, and the second one represents the pitching moment equation. So this is the rotation about y-axis, and the third one represents the z-force equation. We will now focus on the applied aerodynamic force and moment terms in the linearized longitudinal and lateral equations. These represent the perturbed change in an aerodynamic force or moment that results from a non-zero value of a perturbed motion variable, like, for example, u, the component of velocity in the x direction. The aerodynamic force and moments can be expressed as a function of all the motion variables. However, we will focus on the most significant variables, we will use a first-order Taylor series to approximate how the longitudinal perturbed forces and moment vary as a function of these perturbed variables. The force delta x is the change in aerodynamic and propulsive force in the x direction and can be expressed by means of a Taylor series in terms of the perturbation variables. If we assume that delta x is a function only of u, w, delta elevator, and delta thrust, which are the most significant parameters that affect delta x, then delta x can be expressed as follows. Delta x will be function only, this is our assumption, in u, w, and delta elevator and delta thrust. So delta x can be represented as follows. Partial x partial u times delta u plus partial x partial w times delta w, and so on, where partial x per partial u, this term, and partial x per partial w, and partial x per partial delta e, and partial x per partial delta thrust, called stability derivatives that are evaluated at the reference flight condition. The variable delta elevator and delta thrust are the change in elevator angle and throttle setting, respectively. Substituting the expression for delta x into the force equation yields the following. So delta x in the x force equation will be replaced by this expression. So, and the rest of the equation will remain as is, as it was. By arranging or rearranging this equation, we can get the following form. Just to collect all the multipliers of delta u in one bracket and delta w in one bracket, and so on. The equation can be rewritten in a more convenient form by dividing through by the mass m. Dividing this equation by m, we get the following, where xu is equal to partial x partial u divided by m, and the same for xw is partial x partial w divided by m, and so on. The change in aerodynamic forces and moments are functions of the motion variables. The aerodynamic derivatives are usually the most important for conventional airplane motion analysis. Follow these expressions. So these are the most affecting parameters that affect delta x, which are delta u, delta w, delta elevator, and delta thrust, as we discussed previously, and the same for delta y, the same for delta z, but with different affecting parameters. The same can be considered for the aerodynamic moments. So this is delta L, delta M, the pitching moment, and delta N, the yaw moment, and this is the roll moment. So the roll moment is affected by delta V, delta P, delta R, delta rudder, and delta aileron. Okay? And the corresponding parameters are affecting the other moments components. By substituting with the last obtained equations into the linearized equation of motion of the aircraft, we get the following. The first set of three equations represent the
longitudinal motion of the aircraft. In the first equation, this is the x force equation. The second equation is the z force equation, and the third equation is a pitching moment equation. The next set, which represent also three equation of motions, is representing the lateral motion of the aircraft. The first one represent the first equation in the second set represents the y force equation. The second one represents the rolling moment equation, and the third one represents the u moment equation. So these are the set of linearized equation of motion for the aircraft.